Right, so we saw property 1 already was when we multiply terms with the same base, we add their exponents. Now let's look at and try to discover what our second property would be. Let's look at a division problem now. And you might intuitively kind of come up with what our answer should be based off of our previous video. Right, when we multiplied terms, we added the exponents. So when we divide terms, you might already think that maybe we subtract. And if that was your thought, you would be correct. But we can kind of spell it out here. Right, y to the fifth would be defined to be 5y's multiplied together, y to the second. It'd just be 2. And when we're dividing, we know that we can cancel out like terms or like factors here. So the y and the y will cancel, y and the y will cancel. All right, and now we're left with 3 little y's left over. All right, and they're all in the numerator. So the shortest way to write 3 y's would be y to the third power. So yeah, if we have division here, we can just subtract the exponents. 5 minus 2 is y to the third. And I'm going to do another example as well to explain what would happen in the reverse situation. We're going to delve more into this in 5.2 when we talk about negative exponents. But if I'm subtracting, yeah, it should definitely come across your mind that if I'm subtracting, I can probably have negative exponents. I'm going to avoid talking about negative exponents in this section and just approach it a different way. We can spell this out, y times y. Right, when we're dividing, we're still definitely subtracting because these 2 y's are going to cancel out with y's on the other side. Right, we're still left with 3 y's. Right, but those 3 y's happen to be in the denominator. If everything simplifies in the numerator, we're just left with a 1. So in this case, we have 1 over y to the third. So whenever we're dividing, right, and we have positive exponents, I just like to think of it as kind of a comparison. If I'm comparing these two sides of a fraction, right, I'd say the numerator has more y's in it, so my answer is going to be in the numerator. How many more y's does it have? 3. So we're finding the difference between 5 and 2. Same deal here. I'm dividing, so I'm going to find the difference between 5 and 2, and the difference is going to be 3. But where are those extra 3 y's placed? Well, in this case, the extra 3 y's are residing in the denominator, so that's where they're going to be in my answer. So that's going to help me kind of define this, the second property of exponents. So we'll call this property 2. And we'll say, okay, x to the a over x to the b equals x to the a minus b. All right, that's going to be our general form, and it will always work, but it can provide negative exponents. So I'm going to say this is going to be our route to take. All right, if a is bigger than b. So if the numerator has a higher power than the denominator, like up here, then we just subtract them. Yeah, 5 minus 2 is 3, and our answer is y to the third. Right, the alternative generic definition here would be, right, if I'm doing this, I'm going to subtract them, but if my denominator has a bigger exponent, I'm going to want to say, okay, I'm going to use my bigger exponent minus my smaller exponent, and all those remaining x's are going to be left in the denominator, because I have more x's in the denominator when b is bigger than a. So if b is bigger than a, right, we can use this alternate definition. Right? All right, so these are the technical definitions, but in practice, I wouldn't I probably wouldn't advise you to actually follow the definition. I would say you can think of it a little bit easier the way I described before. So for a couple of quick examples, okay, if I was looking at a problem like y to the third divided by y to the seventh, I wouldn't say, oh wait, look, the denominator has a higher power, I have to use this formula. That's not the best way to think about it. You don't want to attribute something to a formula. I think the easier way is just to compare. Okay, which side of this fraction has the larger exponent? The bottom. Right? So I'm still trying to find the difference. So the difference between y to the seventh and y to the third, how many y's are going to be left over if I canceled them all out? Well, I have 4. Right, and where are those extra 4 y's in the denominator or the numerator? Well, the denominator, because there's more y's down there. So my answer would have y to the 4th in the denominator. And if you compared that to, let's do it with, let's do it with 2 variables so we can see it happening simultaneously. I deal with each variable by itself. If I'm dealing with the x's, yeah, I'm dividing, so I want to find the difference. All right, so the difference between 8 and 5, there should be 3 x's left over. Where are those extra x's? Are there more in the numerator or denominator? Right? More in the numerator. So I'm going to have x to the third in the numerator of this answer. Okay, when I look at the y's, I have y to the second and y to the seventh. I still want to find the difference. I'm dividing, so the difference between 2 and 7, or 7 and 2, how much is there a change? There's a change of 5. Right? Where are those extra 5 y's? Well, they happen to fall in the denominator since there's more down there, so I'm going to have an extra 5 y's in the denominator. Right? So I think that's the easier way instead of, I mean, you're definitely following these properties, but you don't have to spell it out and write it out in that format. I think it's easier just to think of it as a comparison. So there's our second property. We can look at it in more elaborate situations with coefficients and everything going on. But what I wanted to point out in this video that I didn't in the last is that bases don't have to be variables. If I had 5 to the 12th power divided by 5 to the third power, let's make it to the 10th power. Right? These are not coefficients. They do not act as coefficients because they're being raised to a power. So since they're being raised to the power, these are both bases. Bases don't change. Right? My x's don't change, my y's don't change. I'm just manipulating the exponents. So if I have 5 to the 12th and 5 to the 10th, right, the 5 is going to stay. It's just how many powers of 5 do I have left over? 12 minus 10, I have 2 left over. Right, so you do have to be careful in recognizing a number. Right? It could very well be a base, right? Or it could be a coefficient. If it's a coefficient, we treat it normally. Right? If I had 12a to the 5th, b to the 7th over 6a squared b, well then yeah, in this case, these numbers are not being raised to an exponent, so these work as coefficients. So yeah, I'm going to want to cancel these out effectively. 12 divided by 6, it's just going to be 2. Right, when I deal with the a's, how many a's are left over between 5 and 2? Well, there's 3 a's left over. And when I deal with the b's, there's 7 b's and 1 b. So how many b's are left over after canceling? 6 b's. And these all happen to be in the numerator because I have a larger coefficient, a larger exponent, and a larger exponent. So all of this falls up in the numerator. And there is our simplified answer. I don't think there's too many other variations of this that could throw a wrench in it, so there's our property 2 of exponents.